A payment service went from 10,000 inserts per second to just 200. CPU pegged at 100%, connection pool exhausted in 2 minutes. The culprit? A single composite index. Let's break down why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover database indexing. A database index is a data structure, usually a B-tree, that speeds up data retrieval at the cost of slower writes and extra storage. Think of it like the index at the back of a textbook. Without it, you'd scan every page. With it, you jump straight to the right page. The default index type is the B-tree. It's a balanced tree where each node holds sorted keys and leaf nodes point to rows. The tree depth grows logarithmically. A billion-row table needs only about 4 or 5 levels. But if your query doesn't match the leftmost prefix of a composite index, the B-tree is useless. Here's a concrete example. The first query filters on both userid and createdAt, so it uses the composite index. The second query filters only on createdAt, the index is ignored, and a sequential scan occurs. The fix is to create a separate index on createdAt. A partial index indexes only rows matching a where condition. This shrinks index size and reduces write overhead. For soft delete patterns, index only where deletedAt is null, the index is 10x smaller. But the query planner only uses it if your query's where clause is a superset of the index's condition. Here, the first query uses the partial index because it includes the exact condition active equals true. The second query uses OR, which breaks the match, so the database falls back to a full sequential scan. A covering index includes all columns needed by a query, so the database never has to touch the table. That's an index-only scan. In PostgreSQL, use the include clause to add extra columns without expanding the tree. This can turn a 12-second query into 3 milliseconds, but use them sparingly because they increase write overhead. Before the covering index, the query did an index scan plus 100 heap fetches. After adding total and status with include, it becomes an index-only scan with no heap fetches, much faster. Hash indexes map keys to a fixed size bucket, giving O1 equality lookups faster than B-tree's O log n. But they can't do range queries, sorting, or partial matches. Use them for small lookup tables like country code to time zone mappings. The equality lookup uses the hash index, but a range query like code, US, ignores it and does a full scan. Hash indexes only support equality. GSD and GIN indexes handle complex data types like JSONB and arrays. GIN is faster for lookups but slower to build. GSD is the opposite. A common mistake is indexing the whole JSONB column and then querying with, which doesn't use the index. The first query uses the containment operator at and benefits from the GIN index. The second query uses, which doesn't use the index until we create a path-specific index on data email. Indexes bloat over time as updated rows leave dead entries. If auto-vacuum can't keep up, the index grows and queries slow down. Monitor index size and run REINDEX periodically, but always use concurrently in production to avoid locking writes. This query shows index size, table size, and bloat percentage. To rebuild an index without locking writes, use REINDEX index concurrently. It takes longer but avoids downtime. This is the same issue we highlighted at the start. Here's exactly why that happened. A payment service started timing out on inserts. The database CPU was pegged at 100%, and the connection pool was exhausted within 2 minutes. A junior dev had added a composite index on userid, createdAt, on a 50 million row table. The index was 12 GB, and every insert required updating 3 levels of the B-tree. Write throughput dropped from 10K ops s to 200 ops s. The fix was to drop the composite index and replace it with a single column index on userid only. For the reporting query that needed createdAt, we created a separate partial index where status equals pending. Write throughput returned to normal. This is the exact index that caused the incident. Every index is a tax on writes. Before adding one, ask, is the query that needs it worth the write penalty? If yes, make the index as narrow as possible. If you have a composite index on userid, createdAt, and you filter only on created at, the index is useless. The leftmost prefix rule means the first column must be in the where clause for the index to be used. Running REINDEX without concurrently on a busy table locks it for writes, causing your app to time out. Always use REINDEX index concurrently in production. Partial indexes require the query's where clause to be a superset of the index condition. Using OR breaks that, so the index is ignored. Hash indexes on high-cardinality columns cause many collisions, degrading performance. B-tree is almost always better for columns with millions of unique values. The include clause for covering indexes is available in PostgreSQL 11 and later. In older versions, you must add all columns to the index key, which increases tree size and write overhead. Always check your PostgreSQL version before using this feature. The article mentions partial indexes for soft deletes but doesn't show the full pattern. Here's a concrete example. Index only rows where deleted at is null, and ensure your queries match that condition exactly. Index bloat is a silent performance killer. The article mentions REINDEX, but doesn't emphasize proactive monitoring. Set up alerts for index size growth, e.g., 20% bloat, and schedule REINDEX index concurrently during low traffic to prevent sudden slowdowns. To diagnose slow queries, start with Explain Analyze. Look for SecScan, that indicates a missing index. Check index size and bloat with the provided commands. Let's run through some common interview questions. How does a B-tree handle concurrent inserts? Page splits lock briefly. MVCC helps. When to use GSD over B-tree for nearest neighbor or intersection queries. How to fix index scan with many heap fetches, add covering columns with include. And a few frequently asked questions. How many indexes should a table have? 510 max on write-heavy tables. How to find missing indexes? Use pgstat user tables and pgstat statements. Can an index slow down select? Yes, if it causes many heap fetches or outdated stats. To recap, every index slows down writes, so index only what you need. Composite indexes require the leftmost column in your where clause. Partial indexes are great for soft deletes, and covering indexes make red queries blazing fast but use them sparingly. Ready to go deeper? Up next, normalization versus denormalization, then acid versus base, then change data capture, CDC. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.